All right, everyone. Today I'm going to share a solution or an analysis for a very interesting probability problem. And I think it's a kind of challenging problem, and it gives you a quite comprehensive coverage of a lot of basic uh, concepts and objects in probability and statistics. And also, can be served as a very good introduction problem for discrete Markov process, which is usually you will see in a more advanced stochastic process class. But somehow, I think this problem will give you a very clear path about how these sort of your high school maybe a competition problem evolve into a more advanced knowledge. Okay, let's start. So you are given six healthy seeds on day zero, and the probability of a seed growing into a flower is 50% on any given day. So one, two, three, four. So which means you need to at least wait for one day to see the seed grow into a flower. And also, the 50% here is given in the problem, but we can also change that probability to see how it affects the result we are going to have. And assume that once we have the flower never dies. Okay, this is actually very useful assumption in my case because you will see that the the expectation date, if it's really short comparing to the lifespan of flower, it's just very practical to do such assumption. And the question is, what is the average or expectation uh, days we should wait before we see six flowers for the first time starting from day zero? Okay, this is very important. Is to see the six flowers for the first time, because say we have six flowers on day 10. So on day 11, we have 100% of a probability to see all the flowers. So this is a very critical thing you need to keep in mind. And also it's really very strongly related to a very important a concept in discrete Markov process. It's called first passage time. So this is something or a measure we always look for if we have a rigorously defined a discrete Markov process. Okay, we will talk about that later. So let's just give you a quick example. For instance, we have six zeros, six seeds on the first day. Okay, so on the second day, we have actually many choices you can think about. Either you can have like all seeds grow into flower, or all seeds just keep in seed form, right? Or some of the seed grow into flower. So there are many cases we can have. So let's, for example, say we have the first seed grow into flower, and everything else, keep the same. This is one possible way. Okay. On the second day, on the second day means we need evolve from the situation we have the first day. Okay. Here is something constrained we have in this new starting from new state, because we can have seed grow into flower, but we cannot have flower goes back to seed. This is not allowed. All right. Uh, we can have seed to seed. This is okay. So these two are okay. The middle one is not allowed. Okay. So for the first one, we can just carry it on. And probably we can assume, you know, this one grow into flower, and this seed just keep the same. And something magic happened on the third day. We have everything turned into flower. So all things turns to flower. Okay. So this is, of course, one possible way for evolution. For this goes from all seed into all flower. So this basically take like 3 days for us to see this 6 flower for the first time. Okay. Then you can try to imagine, you know, if we list all the cases, that will be very, very difficult. Very difficult. And since we only have like 6 flowers here, if 6 seeds here, so what if we have more than 6 seeds, like 7, 8, 9, 10? So it would be nightmare. You know, we just want to list everything by hand. Okay, but this give you very good idea about how the steps are affect how the previous state determines the next step, which is important for us to do that with the computer. And typically, that's something we need to consider for discrete Markov process. In case, you know, some of the probability will change based on the situation we have. So if for exams, if the problem asked in exam, you of course want to find a more direct or faster way to compute it. But in real world, you need sort of a Markov process to simulate something will change in the middle. That's why I just list one step-by-step thing here. This is very important. Keep in mind, and we are going to show that in the second part of the talk. Okay, let's go back to the solution. If we want to find a proper way to compute this case efficiently. Okay, so if you happen to have Mathematica and or Wolfram Language, it actually comes with a very useful function called the probability. This probability will compute a sort of compound case. That's when we are going to solve. For example, the 6, because every seed has certain probability, right, to grow into a flower. We are looking for what happens for the 6 seeds. So eventually we'll have sort of like a compound probability. Okay, so the first step is to understand what's the distribution or the probability looks like for each seed. So here we are going to just quickly review the geometric distribution, and it will give you an idea. So assume you have probability x equal to k. So it means you see the first success on k trials. So if the success rate is p, which means every step, for example, if we have like k equal to 5, so we see the first success on the 5th trial, which means you have failure for all the 4 steps before you. So it's 1 minus p. That's the failure to the power of 4. So assume like we see k equal to 5. So you have 4 failures, and on the 5th step you success. So this is what this equation means. Okay, now let's take a look at our problem. The seed grow into flower with a probability 50%. So which means the success rate is 50%. Okay, so let's see, for example, if a seed grow into a flower on the 5th day. It's 1, 2, 3, 4, 5. So that requires 1 minus p. That's seed to seed rate probability. That's 4. And on the 5th day, it must grow into a flower. That's p. So eventually you have 1 minus p over 4 times p. Okay. So this exactly follows the definition for geometric probability. Okay. So to solve this one, we are going to find sort of a predict for this probability function. This is something we are looking for. What's the criteria we must satisfy for it to show the 6 flowers on the 6th day, 6 flowers on nth day? So let's go back to our simulation. Let's recall that if we want to track all the flowers sort of one by one, that would be very difficult, all right? Let's think other way around. For example, if we see 6 flowers on the 10th day, on the 10th day, 6 seeds, 1, 2, to 10th day. So what's the a probable condition for this, or for all the intermediate steps until we see 6 flowers? What's the possible intermediate states? And we ask the intermediate states with something never changed, regardless how you pick, which seed to grow on any given day. Let's, for example, try this one. This must be a valid one. Okay. So it takes, for example, 3 days for the first seed turns into a flower, and then it keeps flower for the rest of the days. For the second guy, like 5, okay. This guy maybe 4. This guy may be lucky on the first one, and this guy takes a little bit longer. So 9th. So what's the last one? Okay, regardless how you change. So what's the last one? Because you want to see the 6 flowers for the first state. The last one must be 10, right? Okay. Is it possible for us to see, for example, this guy turns to 11th state? Well, you will see it's not possible, because that means if this one, the 4th seed takes 11 days to grow into flower, the n should be 11. So the predict, or the requirement for such thing for n equal to 10 is regardless how long it takes for any seed grown into flower, the max number of all the number must be 10. Okay, so this is the function we have to find the solution. Now you may wonder why I put a n-1 here, but we have 10 here, all right? So this is something quite you will see very often in I think all kinds of engineering, science, or mathematics stuff. We have same definition but different convention. So in Wikipedia, you have K means K trials, and you have K-1 failure. So for example, you see the flower, all seeds turn to flower on day 10. So you basically mean you have 9 failures and 1 success. But the function used in Mathematica for the x means you have x number of failures. So here we need to put n-1 here. And to make it even easier to understand is, for example, let's see a seed. that turns into flower on the first date. So which means 0 day and turns to flower on the first day. So this indicates we have zero failure. And we just do one trial, we success, zero failure. So if you plug 1 inside, you should have like 0. So that's why that also shows you need to put a -1 here, a -1 here, right? So this is basically the idea we have for the probability function. So you may ask why we need to do this, because it's very important that to solve the problem in exams, usually the number and the configuration are carefully designed so you can solve it in a short time and do it manually. But in real world, you probably have a different value for p here, or even different distribution for different seed. For example, you happen to mix the bad seed and good seed all together, right? Or GMO seed or non-GMO seed altogether. So you can change the p here to see how this different distribution or same distribution with different parameters change the affects the final result. Okay, so this is the something, though it looks a little bit tedious, but it gives you very good flexibility if you want to do you want to simulate with some variations. Okay, so once we have that, let's just evaluate the code and to see what we have here. It probably will scare you at the first time. That's the expansion of the probability. Okay, because that's the probability for each n. So it's more or less like this definition. It's px equal to k for something. Okay, so this is usually called probability density function, or if it's for discrete variable, because we are talking about the variable of n, all right, on the first day, second day. So sometimes it's also called a probability mass function. Okay, so these two things are usually interchangeable. So let's see for the first date, if everything turns to flower. So which means it only takes one trial for all the flowers to become all the seed becomes flower. So this is a seed on day 0 into flower. Because all the cases, all the growth with a probability 50%, so you expect to see 1/6 or 1/2 to the power of 6 on the first day. So that's what happens. But if you want to do it more rigorously, you want to change, for example, p equal to 1/3, because the reason is we happen to have the very good case that seed to seed or seed to flower probability are equal. Okay, so if you change that to 1/3, you will see exactly it's like 1/3 to the power of 6. Okay, so let's just keep 1/2 here, and then we are going to find the average. Okay, the average. This is a direct computation based on definition. So what's the definition for the expectations? So this is very easy to understand. For example, you have three people in the first class. 3 people, for example. 3 people in the class 1. 4 people in class 2. The average score for the all the for all the students in class 1 is, for example, 80%, 80. And this average is 90. Okay, what is the average score for the entire grade? Is what you do is you have 3 times 80 plus 4 times 90 and divide by 7, right? So it's 3 over 7 times 80 plus 4 over 7 times 90. So this is called the weighted average. So it really depends on the number of people in each class. So you cannot just add up 80 and 90 divided 2. No, you can't do that. So this is the weight, okay? And this is sort of the number, the count number. So it's the same thing for our case. If, for example, this one determines the probability. The probability, that's the weight, sort of the 3 over 7 and 4 over 7. You know, that's the weight for each n, given n. And this is the actual score. So that's like 80, 90 or something. So here is, if you show that is EX just equal to, it's 1 times P1 plus 2 times P2. Plus 3 times P3. Okay, and so on, and so on. So that's why I add up to infinity. So this is the number we have, and we can convert that into a numerical value. So on average, it takes about 4 days for us to see the 6 flowers for the first date, for the first time, and given that the flower with 50% of chance. And so we can also just change the probability here. For example, 3. So it's like 1/3, okay? And what's the probability that all 6 seeds grow into flower for the first date? So that's 1 over 792, which is 3 to the power of a minus 6. So that's right. And let's see how it affects the average. And make it a numeric. So that takes 6.5 days. Well, which is expected, because if the seed is unlikely to turn itself into a flower, it of course will take longer for us to see all seeds turns to flower for the first time. So this is a really intuitive way and qualitative way to check if our solution is correct or not. It will never show that if, for example, I made it's like 7, instead of 6.5, right? It won't help you figure out what make mistakes in that situation. But if we get like 2 here, we immediately know this can't be correct. Okay, so let's first turn it back into 1/2. Okay, so this is one way to compute the expectation value. The other more flexible way is to use customize the probability distribution function. So this one will actually turn this expression into built-in, sort of like built-in probabilities. It's just like a geometric distribution. So you will see there are many functions that can actually work on this function, like PDF or CDF, to compute the distribution, the actual symbolic distribution, and you can just use like mean or kurtosis, all kind of gauges or measures directly onto this predefined distribution. And we want something just like that. So we can use the probability distribution function. So this is the function that I use here. That one will convert expression into sort of object, distribution object. So the built-in functions, PDF and CDF can directly call the can be called on this on this object. And here we use PDF because we are given this is the PDF, and we know it's a discrete distribution from 1 to infinity. So I put 1 here because it must have step size 1. Okay, so this, if you run that, this gives you a customized distribution. And let's take a look at its CDF. And this is where I realized there might be a simple solution for that, more concise or unexpanded expression for this type of problem. And we will see that clearly once we turn that into a parametric statement. And this one, it happened to be just useful in this case because we assume the P is the same for everyone. But if we have some distribution with different parameters, this won't work. You need something like this to handle more generic cases. And we can just compute the mean value for D, which happen to be same thing as the direct computation. And I will quickly skip D for the later case if we turn to parametric because it's very complicated. But in this case, because we have solid numbers here, it will give you the result in quite a short time. So this is the variance. The variance determines how widespread this distribution is. Okay, and we can, because we already have this D here, we can actually quickly plot this distribution just like we have here. Let's just do that. Because this number only works with 1, 2, 3, 4, 5, 6, and so on. And this is the distribution of D. Okay. And the variance actually measures how widespread of this distribution. For example, if we look at the normal distribution we see quite frequently is normal distributions. So it would give you the idea about how spread, how thin and how fat-tailed a distribution looks like. So this gives you a very good measure about the sort of spreadiness of the distribution. So the smaller the variance is, which means the data points actually gets closer. All right. If it's really large, it means the data sets are kind of more like evenly distributed. So we can also try that with the double plot. One is the plot of the PDF, which is just the distribution of this curve. So PDF is P like x equal to 1, P equal to x equal to 2, and so on. Okay, and the CDF is the cumulative one. It's P, for example, is x equal to 1, and P2 is x less than 2, and P3 is x less equal to 3, which is basically the sum of all the items before 3. So that's P1, x equal to 1 plus x to 2. And if, for example, if we have 4, that's x equal to 1, x equal to 2, x equal to 3, and equal to 4. Okay, that's the cumulative means. Basically, just add things up. Then you can just plot them all together. It gives you the idea about the CDF, PDF that looks like a CDF, PDF and CDF. So this is also quite important if you want to check something, because you for distribution and probability, the maximum is always 100%. So it's 1, right? So you add up all the cases, it should approaches 1. Okay, which I mean approaches because we have infinite cases. For finite numbers, it's just exactly equal to 1. Okay. For infinite one, it's just should look like it just merged to the line one line here infinitely small. And because lots of distribution with exponential decays, so maybe for some moderate numbers, you just cannot tell, it's exactly one or how, it's just close to one. It must be very, very small. So if I look, these plot look like this, it's highly likely it's a good one. It's correct. And now we can just turn it into a parametric model, which is also inspired by this expression. So if you change the p into 1/2, 1/3, you will actually see why it works in, it looks like this, and which is also the CDF, given the CDF. Okay, let's just quickly explain what does it mean, and then you will see why it works. Let's just recall this one looks like 1 minus p to the power of n, and for 6. Okay, let's first look at things inside this parenthesis. It's 1 minus p over n. The reason it works is we say if this flower, if this seed, we can see that on the nth day, it turns flower before the nth day, before the nth way. So maybe it's like this. It takes 3 days, and it turns to flower. For example, on the 4th day, right? On the 4th day. So which means is before the 5th day, you need to have at least it is the success before 5. Okay, so what is not valid is it keeps failing for the 5 days. This is what it means for 1 minus p 5. For example, let's turn it into 5. So this is one valid case for that. One valid case for this 1 minus p. So the only thing that's not allowed is you have no flower for the 5 days. So that's the probability is 1 minus p to the power of 5. So everything else is allowed. And notice you can't have things like this. This won't happen. So this is what this expression means. And this one is for one seed. And now we have 6 seed. So it's because each seed growth are independent to each other. So you have this thing to the power of 6. Right? So this is the whole expression means. And this is the CDF. The CDF, it's not the PDF. It's not the day on day 1. It's the whole thing for the entire duration. So this is the probability we have. And let's take a look at it. Okay. So this is the expression, okay? And we can also just directly compute the mean for that. This will be a little bit more difficult because in this case we have all the everything we used to have, like 1/2 becomes a parameter p. So everything becomes more complicated and requires rigorous process in symbolic computation. And typically we want to make it look like a little bit simpler by taking all the denominators apart from the whole expression. So this requires extra computation. That's why it takes a little bit longer for it to show up. And we want to see if this one works, okay, or not. So we already checked a 1/2 and 1/3. So we can do that again. So this is a 1/2, and recall that 1/3 is around 6.5 days. Let's see if it works. Okay, it works. So this expression is correct. So sometimes if you want to check if the expression correct or not, you just need to do some parameter changes, because if it's something wrong with the expression, it's kind of unlikely for you to check to make it correct for two random points, you know. So this is usually something I would quickly do if I see really complicated expressions. And now we can see the M2, that's the mean, how the mean changes with P. And this is the curve we have. Well, so for example, if we are around 50%, we will see it's around 4.03. That's correct. And as P becomes really small, for example, only like 10% of a chance it will grow into a seed on any given day. So we need to wait almost like 3 weeks for that to happen. Okay. And on the other side, if it's guaranteed to grow into a seed on any day, so 100%. So we need to wait at most 1 day, right? So it's not 0, it's 1. So it's correct. It's 1. Okay. So this is basically what we have for that, and we can also check some of the whole distribution changes given different P. For example, if we have like 12.5% of chance of growing to flower on any given day, this is 25%. This is like 33%. This is 50% as we have in the problem, and this is 75%. And let's see how it affects the graph. And we plot that for 25 days. Okay, so from day 1 to 25. Okay, that's what we have. That's what we have for the distribution. It's slightly different from the plot we had before, because now some of the number are really small. You know, I cannot even see that on the plot we had before. So we need to convert that number, convert the scale on the convert the y scale into logarithm, scaling function log. So, for example, 1 in million, so small if on the regular scale. But if we put it on the log scale, we can actually see that. You know, that's sort of a thing we can see on the scale. And also, this is quite interesting. You know, for really small scale, for really small probability, it looks like flat line on log, which is can be explained clearly with asymptotics behavior, because if we just shrink this probability, we will see it actually getting very close to something like p to the power minus n something. So that exactly gives you a line on the log scale. So let's say what we have for the first case is say we are close to 1. You know, what's the behavior of p close to 1? Because you know, every time if you carry this whole monster expression to compute, it's very annoying. But sometimes we can just make a much simpler expression for that if we know p is at some certain range. So this is a very good case for asymptotic function to be kicked in. So this gives you two approximation for p approaches 1 with first order approximation and the second order approximation. So these two expressions are much simpler. So if I know p is somewhere close to 1, I can use make it just 1, or you know, use a little bit of slightly more complicated expression to show that. And let's see how this one approaches p. How approaches 1? Given the exact formula, first order approximation and the second order approximation. This is the diagram we have. So one is not very good, but the second order is pretty good once we pass like 0.9. So you can have higher orders. You know, even larger range for better approximation. But this one looks good if we assume like P is more than 90%. And what happens if we have P approaches 0? It's very small, right? So this thing actually behaves like hyperbolics. So this is the first order, this is second order. And because we have P very close to 0, so this guy will just vanish very quickly, and everything you will leave this thing. And once P approaches 0, this term will be so large. Think about like 1 over x. X is like 1/100th. This thing is very large. So any constant around it will just be vanishing. So you won't see that. So this is the plot. I make the into two diagrams because this one actually approaches the original one very well. So it won't show up very clearly if I plot all three things all together. So this is the mean for the original, and this the result from the first approximation. So you can see there is something slightly off, for P that is lower than 40% chance. But if we use the second order one, this one is surprisingly good. So it's actually almost touch each other because they match so well. They almost overlay. So if I use the same thickness like this, I'm not going to show you. You actually see two curves on the diagram. So I need to make the mean kind of like the background of the curve for the second order approximation. So you can see they actually just touch each other, 0.9. So which means this second order approximation matches this curve for really, really long area. So this is something we're glad. So we can just probably always carry on this term to show the approximation. And why this one also works so well is, let's go back to the monster expression we have here. Because as P approaches 0, you can see this is somewhere like a constant. It's just -2 plus 0. And this is something we need to keep, right? And this thing is not keep. It must be discarded because P times 0 for that thing is for this part is 0. This part is 0. This part is 0. So it's a constant, and a constant. So the only thing we need to care about is something like this. So this is why 1 over P is really good. And if we add some other terms, it will give you like second order approximation for other terms. It will give you a nice approximation over much longer area. Okay, so far we have covered direct process in this case. And I think it's a good place to stop for the part 1 of this lecture. So before we terminate this video, I just want to go back to the top page. And you see 3 diagrams here. And I'm going to review these 2 in the second part, and just want to quickly explain what's the meaning of the first one. So once we have the M2 expression here, let's go down here. Okay, so this is the expression we have. So in mathematics, just like sine and cosine, what you have learned in high school, you can only plug that with the real numbers. But somehow lots of functions, if we have a sort of a nice expression, though we derive it from sort of probability, we have to have P is between 0 and 1. But, well, mathematicians need some creativity, okay? Sine x, cosine x, you can plug complex numbers in that. Same here. So we use a technique called the domain coloring. So this is a very common method to visualize complex numbers or complex mappings. So we use the same thing here. It's a built-in function called a complex plot. And we plug in M2. That's the mean value. And we cover a much larger area than 0 to 1. So we give it a shot, and we see what's the image of this function over the complex. It's quite nice, and this is the first diagram we have in the cover. And yeah, let's just have a quick break in this lecture, and I'm going to make a second video on this topic, and we'll see how we apply discrete Markov process to solve the problem and give you an idea of the entire concepts behind Markov process. Thanks for listening. See you next time.